All right, good morning, everyone. Welcome to Engr 325, Numerical Analysis Techniques for Engineers. So this is the first class meeting. Last week I was still trying to figure out when and where we were going to meet, trying to coordinate everyone's schedule. So in the meantime, first thing you'll notice on the syllabus was a programming review. So everything that we're going to be doing in this class, I'm going to be doing in Visual Basic. Uh, VBA, the reason why I like VBA is because it's accessible to everyone. Almost everyone has access to it nearly 100% of the time. So if you're on any Windows machine, school, work, whatever, usually you have access to Microsoft Office. So if you need to go in and run a real quick script, just go into Excel, run the script. That way you don't have to worry about having administrative privileges, trying to get someone to install a compiler and do all those sorts of things. So I like it because it's a really easy language to get to. It turns out that's important if you learn some esoteric language, even a more powerful language, say like MATLAB. Okay, well that's fine, but when you go out into the real world, okay, good luck with that. If you can get your company to buy a copy, okay, maybe you can, maybe you can't. So that's why I use Excel. So I gave some lectures on programming review. Um, Basically, here's a playlist that includes all. I taught Visual Basic in the past, so this is a playlist that basically teaches you almost everything you need to know about Visual Basic. So instead of you having to go through everything, basically what I identified was about 8 tutorials that you probably need to go through if you're kind of rusty on Visual Basic or you don't know the language at all. You should know at least some programming, and it's pretty easy to learn. Okay. And then I gave a couple lectures on basically how you can use programming to approximate transcendental numbers. Um, did I give yeah, gave a video also on transcendental numbers. So if you haven't watched that video, watch it. It's pretty cool. This kind of changes the way you think a little bit about numbers. So here was two lectures. One, how do you approximate pi? So I showed the code how to do that. Two, calculation of transcendental functions, so like a sine function. So to be honest with you, most people go through college using sine, cosine, tangent, log, that sort of thing, and they never really know where it comes from. It's just, oh, we just hit your sine button on there and make sure you're in radians or degrees, and the sine of whatever gives this. It's like, well, where does that come from? Well, I don't know, just does. Or even like where pi comes from. Where does that come from? Well, I don't know, just kind of 3.1415, just kind of used it my whole life. So I think it's a good exercise to really do that work, and then you have an appreciation for what it is you're actually using. So you take something like, the natural log of a number, what is that really? Well, it's e to whatever number it has to be to equal that number. So, if you take the natural log of, I don't know, 56, what's the natural log of 56? Well, it's the exponent of e to x equals 56, whatever x is. So how do you calculate that? Well, you hit ln on your calculator, and you get your answer. Um, if I go in and take 56, take the natural log of that, well, I think that's base 10. Uh, I don't see the natural log button on this. Drives me crazy. Who uses base 10? Let's see, scientific. This probably isn't the best calculator. Does anyone see it just drives me crazy. The Windows, Microsoft, they just can't help themselves. They used to have a great little calculator, and then they had to go in and change it, I guess so you can touch it with your fingers. Um, but it used to have natural log and all that sort of stuff, and now it doesn't. So there you go. take natural log of 56. What do you get here? You get 4. So e raised to about the 4th power gives you 56. All right. So how do you calculate that? Well, you see it says natural log 56 is a transcendental number. I show how you actually calculate that in these modules. Okay. So today, what we're going to learn about, I originally had in solutions of nonlinear equations. And then I got to thinking, well, you know, before we can actually use these methods, one being Newton's method, which I'll talk about a lot in this class, we have to know how to take the derivative of a function. It's like, well, I'm sure everyone in here knows how to take the derivative of the function. But then I was thinking, but in this class, to be honest with you, taking the derivative of a function, the purpose of numerical analysis is to keep out of symbolic notation, okay? So when you take the derivative of a function, okay, you have to know how to do that symbolically, which we all should know how to do, but I want to teach you how to do it numerically. So I decided to change today's lecture to numerical differentiation for one variable, and then next week we'll talk about how we take the numerical derivative for 2, 3, n variables, okay? All right, so the first thing we're going to do is we're going to discuss what a derivative is, okay? So somebody tell me what a derivative is. It is a tangent line, okay? So that's exactly right. So if we take the derivative of x squared, so let's suppose we do this. Let's suppose we plot the derivative of x squared along with the actual function, say from -10 to 10. Is everyone familiar with Wolfram Alpha? Okay. If you're not, go to Wolfram Alpha. Get familiar with it because we're going to be using it a lot in this class. So you see this is our original function, x squared. And the derivative of x squared is 2x. How do you do that? You pull the 2 down front, take, the derivative of x to the n equals n times x raised to the n minus 1. All right. So we all get that the derivative of a function basically tells you the slope of that function at any given point, right? Easy enough. We all remember how to do that. And so then what's the second derivative tell you? It tells you the slope of the first derivative. Okay, so you can just keep on going if you wanted to. All right. So what we're going to do today is I'm going to go over just a very brief notation. So this is the way it works. There's different notations. If we have, say, the function, say, y equals x squared, okay, then dy over dx is equal to 2x, right? And then d squared y over dx squared is equal to what? It's equal to just 2, right? All right, so this is called, I think, Leibniz notation. Lagrange notation is if you have f of x is equal to x squared, then you have f prime x is equal to 2x, and then f double prime x is equal to 2. Okay? Let's get that out of the way. I know you guys know how to do that, but still just want to write it down. All right? So that way you'll see where I'm going with that. So this is the fundamentals of calculus. All right, so I just wrapped up the entire Calculus 1 course in 3 minutes. Okay. Okay, so what we want to do then is we want to determine how we can go in then and numerically calculate the derivative of a function. So does anyone know what I mean by when I say numerically calculate? Basically, it's an approximation. So let's suppose that I just give you a function, all right, and the function looks something like this. And I tell you that I want you to calculate the slope at this point. So the only thing that I give you is basically a data table. So I come over here and I say, all right, this is my x value, this is my y value, so I have something like 1, 2, 3, 4, 5, and then I have 0, 1, 4, 9, 16. Okay, but this is all I give you. Well, you may look at this and say, okay, well this is x squared. I'll just use x squared. But let's suppose that I don't tell you that these numbers are something like 1.2, 4.6, 8.7, something like that. And all you know is basically just what the curve is, just from data. All right. Now, this happens all the time if you're actually experimenting with something. So if you go in and you're actually doing some type of experimentation where you want to see the response of A versus B, okay, I don't know, maybe you're going over in the testing lab and you're pulling apart some type of metal, and you're just looking how much tension there is on that, and you're graphing that over time, all right? Well, you're going to get a graph, but the computer's not going to spit out that equation. It's just going to spit out, very small increments of time what the graph looks like. Now, you could go in and maybe try to fit an equation to that. We'll talk about that in class. But what you're essentially given is this. Now, when you see it as a graph, you're like, no, I'm not given this. It's giving me a graph. It's like, no. It's giving you this. And then it's just plotting that, all right? So if you need to go in then and determine some information about that, maybe it's some type of, it's a dynamics problem and you're looking at how something is how fast it's traveling over time or just whatever it may be, and then you're wanting to take, say, the first derivative information to calculate velocity from acceleration and vice versa, that sort of thing. You're not actually given the function, all right? You're not given that. You're just given data. So if you want to go in and start looking at first and second derivatives, what you have to do then is start using some numerical techniques, hence the name of this class, numerical analysis. So what you're going to do is you're going to go in and you're going to create an approximation for that. All right, so if you recall, when you first learned calculus, and you may not recall this, but let's suppose that you had, a graph that looks something like this. All right. Do you remember how they actually taught you how to calculate the derivative? Basically what they had you do is they had you pick one point, okay, then you took another point, and then you basically calculated the rise over the run. All right. And then you actually learned the numerical part of calculus first, but they probably only talked about it for just like a lecture. Okay, so you had your delta y over your delta x. Okay, rise over run is basically what you get. So that's really all there is when it comes to calculating numerical derivatives. So what we're going to do is we're going to go in and we're going to write a little program that's going to do this for us. So let's go into Excel. Okay. Now, your Excel may or may not have this Developers tab. Okay. If it doesn't have the Developers tab, what you've got to do is you've got to go over here to File, and then you go down here to Options, and then you go to Customize Ribbon, and then you make sure this box is checked. All right. That's all you do. And then when you hit OK, you get this Developers tab. Does everybody have the Developers tab? Okay, question. Does everyone know a little bit about Visual Basic Programming?
Look. Go over that one more time.
Sure. File, Options. You'll go to Customize Ribbon, and then you'll make sure that the Developers box is checked. Okay. So did Bolton have you guys do anything in VBA?
Yeah.
Oh, okay, kinematics, that sort of thing. Okay. All right. So, do you have that? Okay. So now what we're going to do is we're going to come up here under Insert, and we're going to come down here under ActiveX Controls, and we're just going to make us a little button. All right, that's all we're going to do. It's just a button. And then you right mouse click on this, go to Properties, and we're just going to name the button. I mean, you can name it anything you want. I'm going to call it, let's call it First Derivative. You can't put a space in there either. Not for the name. Now for the caption, I'm going to call it First derivative, okay, with the space in there. One is the actual name, the other is just a caption. You could put bananas or anything you wanted on it, okay? All right, so we've got us a button. All right, now if you double click on this button, it's going to bring up this window, and it's called up here private sub first derivative click. So whatever is in whatever code we have in this module, when we click that button, it's going to run. Okay. All right. Now, before we get started with this, I'm going to go down here, and I am going to define a function. And the way I'm going to do that is I'm going to type in function, and then I'm going to say f of x by VALX. Okay, and then I'm going to hit enter. And all this is doing is this is just allowing us to call a function that we define from our main code. So if we want to change the equation that we're going to be working with, instead of each time having to go into the main code and change that, we can just change it in this module. And I'm just going to comment, I'm going to put a little quote there, and I'm going to say define function here, and all this is just comment, so it's not really doing anything. And then I'll say must define function in the following line. Okay, and this just helps you at some point if you go back and look at your code. It's like, what was I doing there? Oh, okay, I see. And then I'm going to say f of x is equal to x squared. And I think you have to put spaces between them. Okay. So we're going to start off with using x squared. That's the function. Now, you notice that I put f of x, but I could put like anything here. Call my function Shannon, and then it would be like Shannon equals that, and then I would call that. But that's kind of dumb. So that's why we use f of x. But you could use g of x, h of x, whatever you wanted to put there. Okay? All right. So let's get started. Now the first thing we're going to do is we're going to come in here and we're going to declare some variables. So I'm going to declare, the way you declare is just called DIM. It's just the notation of Visual Basic. I'm going to say X step, comma, B slope, comma, F slope, comma, C slope, comma, Y naught, or I'll just say Y, you can say Y0 and Y1. Okay. Now, you may say, what are all these? Well, I put in a whole bunch of things because we're going to use them because I'm going to show you 3 different ways to do this. Initially, we could have started out with just X step, B slope, Y naught, and Y1. Okay? So I'm going to come in here and I'm going to say X is equal to val. The reason why I put value, a lot of times when I'm working with numbers, when you put val in front of something, it forces it to be a number. Because sometimes, it'll make it a string for. So that way, if it sees a number or anything, it just says, all right, this is a number. Val input box, okay? And then I'm going to say input, I've got to put a quote, input value of x to evaluate derivative at, quote, like that. Okay, let me see what I've done. Oh, got another parentheses like that. And then I'm going to say step is equal to VAL dot or input box, and then I'm going to say input step size. Input step size. Okay. So this is all I've done so far. I'm going to go ahead and save this, and I'm just going to save it. I'll save it on my desktop real quick. Maybe. Okay. Save it on my desktop, and I'm just going to call derivative. And you've got to make sure you save it as an Excel macro-enabled workbook. Okay? Save it. Okay, let me go back to my code. All right, so all I've done so far is I've put in, if I run this, click up here on this, it's just going to bring up two boxes. And so where do I want to evaluate my derivative? 3. And what do I want my step size to be? 0.1. Okay, that's all it does. So here's what we're doing. Really simple. Is we're saying, where do we want to evaluate our derivative? Right here. That's what the first box does. What do we want our step size to be? What do we want our interval to be, basically? It's this delta x value. So step is going to be equal essentially to delta x. Okay? Now, the smaller delta x is, the closer you're going to actually get to the true derivative. Do we all kind of understand that? All right. So the first thing we can do is we can calculate what's called a backwards derivative. So I'm going to put a quote here, and I'm going to say calculate backward derivatives. Okay? Now what does this mean? Well, here's what it means. It's really simple. It means that if I have a curve, okay, and I want to calculate the derivative at this value right here, the way I'm going to do that is I am going to go backwards. All right? This much. Okay? So my delta x is going to go in the back, negative. So if I'm evaluating at x equals 3, and my step, or my interval, is equal to, say, 0.1, what I'm going to do is this. I'm going to take the value of 2.9 and then evaluate that. So if I take 2.9 and square it, what do I get? Can you calculate that for me real quick? 2.9 squared, 8.41, and then 3, 9. So what do I know here? Well, I've got 2 points. What can I do with 2 points? Calculate slope. So how do I do that? I take rise over run. So what do? I take 9 minus 8.41 divided by 3 minus 2.9. So can someone give me that? That's going to be, what, 0.59 over 0.1? 5.9. All right. So if I have the function f of x is equal to x squared, then f prime of x is equal to what? 2x, right? And if x is equal to 3, then what's 2 times 3? 2 times 3 is equal to 6. So do you see how 6 is very close to 5.9? All right? So that's what I did. I calculated backwards. So how do I go about doing this? Well, it's pretty simple. What I'm going to do is I'm going to say, well, my y's not calculation is simply going to be f of x. Now you notice how it said now by variable because I've already defined that. I'm going to type in x minus step, okay? And then y1 is simply going to be f of x at the value of x. So that's just how I calculated. So let's go in and let's step through this. So I'm going to say step into, and I actually have to do this. Normally I'd hit F8, but my recorder uses F8 as the hotkey, so I can't do that. So I'm stepping into my code. It says, all right, plug in a number. All right, I'm going to plug in 3. Okay, 3. All right, let's step into it again. Plug in another number. Oh, let's do 0.1. That's going to be my step size. All right, now I'm going to step into. So let's see, what did this value, well, I've got to run through. Step into. All right, so y naught is equal to 8.41. Everyone see where that came from? Because I'm simply evaluating x minus 0.1. So I'm actually evaluating down here, plugging in that value of, uh, what did I say it was? 2.9, right?
So, could you make another line of code that just says input box Y1 and would it show you on if you hit run?
You mean an input box or a message box?
Message box.
Yeah. So I could actually do that. I could come down here and say MSG BOX Y0, and then I can say MSG BOX Y1, and that's a great idea. Let's run it. And so when I run it, I'm going to get 3 and 0.1, and we get 8.41, and we get 9. Okay? So yeah, that's an even better idea. So does everyone see basically where these two numbers came from? Really simple, right? Nothing hard about this. So I'm just going to delete these message boxes. So even if you don't really know Visual Basic that well, I think you're going to learn it just by observation. So far, this is pretty simple, right? Everyone agree? All right. So now we need to calculate the slope. So this is what I call B slope, which is for backward slope. That's going to be equal to what? Well, it's going to be equal to y1 minus y naught divided by 2 times step. Okay? Now, normally, if you recall calculating slope, it's y1 minus y naught divided by x1 minus x naught. But we don't need x1 minus x naught in this case, because what that is that is the step. But we actually know what the step is. And I'm sorry, it's not 2-step, it's 1-step. I got ahead of myself, okay? It's just step. So do you understand that x1 minus x naught is just step? That's what it is. Normally you have x1 and x naught, but in this particular case we had x naught, or x1, and we actually calculated what x naught was from that, all right? But if we were to subtract the two out, we're just defeating ourselves because we calculated one from the other, and now we're calculating it back. Everyone get that? Super clear? All right, so now all we're going to do is we're just going to say MSG BOX. I'm going to say B slope. All right, and let's run it and see what happens. 3.1, and our slope is 5.9. Simple? Now you know why engineers should teach calculus, right? Because that's what we want. We want a number. Okay, so now let's calculate, and I'm a big fan of plagiarism, okay, actually. Plagiarizing my own work. Highlight this, Control C, Control V, and let's calculate a forward derivative. Now, can anyone imagine what a forward derivative is? Instead of going backward, you go forward, right? So how do you think you go forward? What do you think I put here instead of a minus? What do you think I put? I put a plus. All right. And then I put MSG instead of B slope, I put F slope for forward slope. All right? And
don't you have to change the B slope above?
You're right, I do. All right. So let's run it. 3.1. Okay, 5.9 backward. Oops, I'm sorry. What do I got here? Oh, because I'm going forward now, I need to go y naught minus y1. One little detail there. I had to reverse those. Or maybe not. Let me do it like this. Let me do this. Let me say that this is f of x, and then let me say y1 is f of x plus step. That makes it a little clearer because that way that shows that I'm going forward. Okay. Basically, what that's saying is y naught is always smaller than y1. All right. All right. So now if I run this, 3.1, 5.9, 6.1, roughly.
So essentially, it's the same answer, just one had a negative symbol. We can like negative 6.
Yeah, I just had it. You got to think about it. Oh, now I'm going forward, and where I didn't. Yeah. Okay.
Gotcha.
Got it. Okay. So we know the true answer is 6. All right. So let's do this. Let's make this 3 and then 0.01, and watch what happens. Oh, 5.99, 6.01. So you see how the smaller I make my step or my delta x, the closer it actually gets to the real answer. Got that? All right, now I'm going to calculate one more thing. Okay, so we've done forward, we've done backward. Do you have any idea what else is left to do? We went forward, we went backward. What'd you say? Well, two-dimensional. It can't come out of the... Let's do what's called a central, which is you go backward and you go forward. So you do it like this. You've got a curve here that looks like this. You pick a point right here, and then you say, oh, I'm going to pick a point here and pick a point here and connect those two lines and basically leave. So what I've done in essence is you take the average between the backward and forward is essentially what you're doing. So the area you get from going backward and the area you get from going forward, you kind of let those even out. So let's think about this just a moment. If I plug in 3 and then 0.1, what's the real answer at 3? It's 6, right? 5.9. 6.1. What do I get if I average those two? 6. Well, I got this point like 901. So it's not quite, but it's close enough. Okay. So what we do then is we say Control C, Control V, calculate central derivative. And the way we do that is we simply say f of x minus step, f of x plus step, and then this is where that 2-step came from a minute ago, where I got ahead of myself. Okay? And then you say, I'm going to say C slope for central slope, message box, C slope. Okay? And that's all there is to it. I just taught you how to calculate forward, backward, and central derivatives. So I'll save it. I'm going to run it. I'm going to say 3.1, 5.9, 6.1. Oh, that's pretty darn close. And that step size is actually a pretty large step size. 0.1 is actually, I mean, we often talk about epsilon. Epsilon really usually means a really, really small number. Well, 0.1 relative to 3 is actually not that small. I mean, it's 1/30th, but that's not like super small. Imagine if I come in and I type in something like 3.01, 5.99, 6.0999. Well, still pretty close. 5.9999987. Okay? All right? Now, a lot of times when you're dealing with other programs, like, so let's suppose you're using Solver. Okay, if you haven't used Solver, you will at some point in operations research. And you go up here under options, and you look at, like, say this is the GRG nonlinear convergence, a lot of times under settings, you'll actually see like what it'll ask you, what kind of derivative do you want to use, a forward, a central, a backward. So anytime you see this along the way, that's all it's referring to. Is it's just, are you calculating the backward, the forward, or the central derivative? That's what it is, okay? So I just taught you how to do numerical differentiation. All right, okay, that's good. Now, let's suppose that we have to take the second derivative. How do you think we'll calculate the second derivative? Because the second derivative, it turns out, it's important too. Um, so, for instance, if you have, let's suppose we have this. Second derivative of x cubed, x cubed, x cubed. Okay. That might be to work. There we go. All right. So my original function is this function here. Okay. My first derivative is this parabola. Okay. Right. And then my first derivative is the parabola. My second derivative, what does that tell me? Does anyone remember what that tells you?
It's accelerated.
It tells you kind of if it's concave up, up, down.
Yeah,
Remember
yeah,
how
yeah.
that? And then like 0 is, it's like if you were to plug in 6x, right at 0 it is 0, so it's not up or down. That's the actual inflection point. But if I look at 6x, anything above 0, like say at 1, it's positive. Anything below, it's negative. So it's telling you literally, basically, that everything here is concave down, and then here is concave up. Okay? And then like if you have a x to the fourth, then it would always be positive. Um, so that's what that tells you. So second derivative information, we're going to find out. Have you guys done a lot of work with second derivative information? So you've used second derivatives? Yes, no, maybe. I've heard of them.
Back at Whitfield, we did.
Back at Withful. What did you use them for anything?
We used it to determine something.
Okay.
I can't remember exactly what. It's been a while since we messed with them, like calculus.
Right. What it does is it basically, some functions, if it's always positive, that means it's a U-shaped function up. If it's always negative, it's a U-shaped function down. If it changes, it tells you the inflection point. And if you set that second derivative equal to 0, it tells you where that inflection point is. So in this particular case, if you look at your second derivative, 6x is equal to 0, right? Well, x is equal to 0. So that tells you it tells you basically where your slope is equal to 0, basically. So where it goes from negative to positive shows you what's called the inflection point. Okay? Now we're going to see why it's important when we get into using numerical analysis. Okay. All right, so how long was this class going to go? Was it going to go 50 minutes or an hour and 15 minutes? What was the plan?
That I don't remember. I just remember.
Yeah.
Do you guys have a time constraint?
Not really.
Not really. You want to go a little bit longer? Okay, learn some more stuff. Okay, so now what we're going to do is we're going to go in and we're going to see how we numerically calculate the second derivative. Okay? So let's do this. Let's come over here and let's make us another button. So you have to make sure developer that you're in design mode, and then you can you know, copy this and then Control V and paste it. Okay. And then right mouse click and go to properties, or you can just create a new button, but I'm just extremely lazy. And I'm going to call this second derivative. Okay. And then the second derivative, like that. And now when I double click on it, it's going to bring it all up in here in the same module, but you just notice it's called second derivative. And periodically I like to hit my save button. All right, because what will happen is sometimes you'll do like a Fornex loop, and that sucker will run away with you, and you'll lose your work. I've had that happen more than once. Okay. Okay, so what I'm going to do is I'm going to come up here and I'm going to grab like just this part right here, the first 3 lines. Control C, I'm going to paste it down here. All right, so instead of just having 1 step, I'm going to have 2 steps. I'm going to have step 1 and step 2, okay? And then I'm going to have what I call CB slope and CF slope. And then I'm going to have something that I call just slope 2 for second derivative slope. All right? And then I'm going to come down here. I'm going to have this, I'm going to call it step 2. I'm going to say input second step size. Second step size. Okay. Okay. So now we have to think about this just a second. Why do I have 2 steps? I have step 1 and step 2. All right, well, let's think about this. Got this curve that looks like this. And I want to calculate my second derivative. So what that means is I'm going to calculate the slope of the slope, right? So when I calculate this tangent line, it looks like this, right? So then on that tangent line, what I've got to do is I've got to move over, say forward and backward. And then I calculate what the slope is from these 2 points. Okay? Does that make sense? So I have 2 slopes. The first step is to actually calculate the derivative of the first derivative. And then the second step, step 2, is to establish a second interval on that first derivative curve. All right. So when you look at this, and I'm looking at it from a x squared and then a x 2x, it's a little bit harder to see because it's like, well, but the slope isn't changing. It's like, exactly, the slope's just going to be 2. It's a constant slope. But if you have some function, say like the natural log of x or something, where that first derivative isn't a straight line, it doesn't remain constant, then that will actually change. Does that make sense? A little bit. I mean, you can really see it if you plug in something like I don't want to use the natural law. Well, this is it if you think about it, because this first derivative. So here's what you have to imagine then. Here's what you have to imagine. I have my original function. I calculate then the first derivative, and then I throw away my original function. I don't even know what it is. Who cares? Then I go in and I calculate the slope on my second function, right? So if you think about it, you kind of say, all right, all I'm interested in is this second derivative curve. And how do I get rid of that? Well, it's simple. I just delete this sucker. I went the wrong way. Oops. There we go. Let me delete my original one. There we go. So I don't even know now what my original function was. All I know is what the second derivative was, and then I calculate the derivative of that. Okay? So the way I go about doing this is I have to have two steps. All right? And then I'm going to come in and I'm going to say, let's calculate backward central derivative. Okay. Okay, so think about this just a second. Is I have used, instead of calculating backward and forward derivatives, what I have decided based on the information that I acquired is that central derivatives are better than forward and backward derivatives. Does everyone kind of see that in general? That they seem to be better because you're taking the average of the forward and back. So I can just throw these away. I'm not going to calculate central or I'm not going to calculate backward and forward derivatives anymore. Everything I do is going to be central derivatives. Okay. But now I'm going to go in and I'm going to calculate the backward central derivative. So what that means is I'm going to use the central derivative approach to calculate the actual slope of my first derivative. But now within that first derivative, I'm going to go backward, okay? And then I'll go forward, and then you'll see that. And so basically I'm calculating a central derivative. Does that make sense? Or is that just totally like, what's he saying? Do you get it? Okay, do you get it? You get it? Sort of. Okay. So I'm no longer using forward and backward derivatives. I'm just using central derivatives from this point forward. All right. So now, because I feel like that gives me the best estimate, so now I have to calculate the slope of this first derivative line, okay, using the central derivative algorithm that we established. So then how am I going to calculate the slope of the slope? Well, I could use the backward, I could use the forward, but why not go ahead and use the central? So I'll use the central derivative approach on the central derivative approach, okay? All right. But before I can calculate a central derivative, I have to calculate the backward and the forward. So the first thing I have to do is calculate the backward part of the first central derivative, all right? Now, if you're getting a little confused, don't worry, because it's all going to fall together, I guarantee it. Okay. So how am I going to do that? Well, what I'm going to do is I'm going to say xb for x backward is equal to x minus step 2. And then I'm going to say y naught is equal to f of x of xb minus step. Okay. And then y1 is equal to f of x of xb plus step. Okay. And then my central backward slope is going to be equal to CD slope, central backward, of y1 minus y naught divided by 2 times step. Okay. Now let's calculate the forward. Calculate the forward central. How do I go about doing that? Well, I'm going to say instead of XB, I'm going to say XF. I'm going to say XF here, XF here. Okay. And I'll say this is central forward. Yep, that's what I need. Now I'm going to come down here and I'm going to say slope 2, which is my second derivative slope, is equal to CF slope minus CB slope divided by two times step 2. Okay, and then I'm just going to say MSG of X. I'll just say like central derivative equal and slope 2, something like that. Okay. All right, so that's all perfectly clear, isn't it? So I'll explain it. CD, okay. All right, so let's do this then. Okay. Let's think about this just a moment. Let's go in here and let's suppose I have f of x is equal to x cubed. And I want to evaluate at x equals 3. All right. So that means f prime of x is equal to what? 3x squared. All right. So f of x, f of 3 here is going to be equal to what? 27. So f prime of 3 is equal to what? 18? Right? Is that right? X squared, 9. So f double prime of x is equal to what? 6x. So f double prime of 3 is equal to, in this particular case, it's also 18. All right. Did I get that something wrong?
Isn't f prime 27? Because it's 3, so 3 squared is
You're right.
9.
I thought that there was something, yeah, 27, right?
Yeah.
Yeah, I'm sorry. Yep. And it's just because I picked 3, it turns out that these two are the same, just coincidentally. Okay? But what we should get is we should get their second derivative should be equal to 18 when I evaluate 3. Okay? So let's plug it in and see what happens. Let's cross our fingers. Second derivative, put in a value of 3. I'm going to put in a step size of, say, put in a step size of 0.1, and another step size of 0.1. Okay, what do I got? Okay, that didn't work. Let me see real quick. Okay. That's always great when it doesn't work. At least you know where you stand. Oh, no, that's not it. Alright, XB, step 2, step 2.
Do you have to change the FC slope?
Where do you see this?
Because it says equal to y1 minus yo, which is the same as the BS slope, or the CBS slope.
Where is it right here you're talking about?
Up one.
No, up one.
This one right
That
here.
is the same as the CBS slope equation.
Okay.
So does that cause a problem?
Um,
Because wouldn't you want to add the support stuff?
so what are you saying that I need to put in there?
I don't know.
Say replace the minus with the addition.
No, you have to change Y0 and Y1 position.
You have to change the position.
I mean, maybe.
Let me try that. I don't know that that's right, but let's try it and see what. Oops. Okay, let me see what I did. 3.1.1. Definitely changed something. I don't think that's it though. Okay, let's see what I've got here. Two. X of F. Let me go back here. It's really hard to step through on this computer. Let me do this. Let me cheat. And I hate to cheat, but hey, sometimes you're up against it. That's all you can do. I mean, I know it works because I just wrote the program. But I'm sure that I've got a mistake somewhere. Let me run this real quick. Oh, guess what? I actually know where the mistake is. I don't even have to cheat. You're going to love this one. Oops. Okay, it's real simple. I forgot to change my function. I had x squared, but it needs to be x cubed. Yep, that'll get you every time. I thought that was the problem. It's something really simple, I have no doubt about that. It's something really simple, I have no doubt about that. Okay, developer, sign mode. Okay,
I'll change that, right? I'm getting divided by 0 errors still.
3.1. Oops. Wait a sec. Oh, okay. 3.1. Okay, I'm getting the right answer here. So let's figure out what we've done wrong. Okay, what I did in this particular case is what I was going to show you is, let me try what is different. So what do you guys have? You've got all this up here, right? Let's see what happens. So if I plug in a value of 3 and 0.1, CB slope, so there's something that I did wrong. Try to help me find what is different. So what do you guys have? You've got all this up here, right? So then you get xb equals x minus step 2. You got this right here, is that correct? And you've got CB slope is equal to this. Is that correct?
Yeah.
Okay, then you're going to calculate xf equals x plus step 2. And then down here you go y0 is equal f of x, ff, xf minus step, y1 xf plus step, and then cf slope. Is there a problem there?
I got BS on
BF?
the
Point one, point one.
overflow.
Really?
Yeah.
Huh. Let's see. And then you make sure you've got your f of x is equal to x raised to the third power. Okay?
Mm-hmm.
Okay. All right. Well, let me run it one more time, make sure it works for me. So I plug in one more time, make sure it works for me. I'm going to take this and highlight it and Control C it, and I'm going to come up here under what I'm supposed to get, and I'm going to come up here under Moodle under Working Document, and I'm going to paste this in so you guys can see this. So come here and copy and paste that and see if it works. If you have your Moodle up. So this allows us to work kind of collaboratively. Yeah, it's under the very top. It's called Working Document. So you can just come here and copy and paste this. Okay. Oh, I think I see the problem.
Okay.
I think I see the problem. Ah, not. Ah, not. Let me try this. I don't think that should matter though. Copy and paste that and see if the code works in yours. Okay, it still works. Um, this should say y, actually y0 and not y little o. So that's something you have to be aware of.
That works.
It did work? Okay. There may be, I may have made a mistake somewhere where I put y little o, because I did that in my original code and I went back and fixed it. So did everybody get it to work? Okay, it did work. So I knew it would work. It's just I couldn't figure out literally, let me see where my mistake is, if I can find it really quickly in this code. Look, when you find the mistake, it is usually something like so simple. Oh, I see it. Right here it is. This should say plus, and I had minus. Try it now. 3.1.1. There we go. Something that simple. I accidentally had a minus here instead of a plus. Where I copied and pasted it, I forgot to add. So is it working for everyone? It is? Okay. Yeah, it was just this one little sign. All right. Okay, so do you understand what's going on? Is it clear that we're essentially calculating our first derivative and then using a central derivative approach. And then we're calculating the derivative of the first derivative using a central derivative approach. Okay? So it's the central derivative using the central derivative. All right? So if you think of the central derivative approach, that's your approximation that you're using. So you're just basically using it twice. So what I did is I said this, all right, well, let's just let step 2 equal step, okay? And then I'll just comment this out. So instead of having to put 2 steps in, I just put 1, okay? And so I put 3.1, and it gives me basically the right answer. But do you see why you actually do need 2 steps? Because you're using 1 step to calculate your first derivative, and then theoretically you could be using another step to calculate your second derivative. But usually that's going to be a pretty small number, epsilon, so just go ahead and let it be equal to let them be equal to the same. Now, okay, so just kind of a heads up though, second derivative information sometimes is kind of harder to calculate, especially if your function's doing kind of something weird, right? All right, so that's basically what I wanted to cover today, so I'm not going to keep you guys any longer. So do you kind of have a pretty good feeling now of how numerical derivatives work? It's actually pretty simple. So this is really going to set the stage for the class. So what I'll probably do is give you guys an assignment for next week, and then we'll come back in and talk about it. So what I'll probably have you guys to do is write a subroutine to calculate the third derivative. Okay? So that shouldn't be too hard. All right, and then we'll talk about it next week. And then next week what we're going to do is we're going to talk about how to calculate numerical derivatives in multiple dimensions. Okay? And then we'll get into talking about how then we can use numerical techniques. And just to kind of give you a heads up, and this is the classic problem that I give everyone, is so what is x? Has anyone ever solved an equation like that? Never saw one. All the math that you took, never saw an equation like that. No, I'm saying that it turns out it's something very simple. You usually never cover how to solve a problem like this. But that's what we're going to be covering in this course. How do you solve a problem like that? And the way you do is you use numerical analysis. Okay? And so that's why learning all this kind of sets the stage to solve basically intractable problems. Okay? All right, well, I'll see you guys next week, and I'll post some material online, and then next week we'll really get into it.